Dear learners, in today's session, we are progressing to the foundation introduction and types. We will explore the fundamental principles of foundations, including their purpose and importance in construction. We will cover different types of foundations such as shallow foundation, deep foundation and specialized foundation like strap footing, raft foundations. This comprehensive overview will equip you with essential knowledge to select and design appropriate foundation types, ensuring structural stability and longevity for construction projects. We will discuss the following key points: introduction to the foundation, causes of differential settlement, functions of foundation, essential requirements of good foundations, types of foundations. So, first is introduction. Every building is composed of two fundamental components, the superstructure and the substructure, commonly referred to as the foundations. The superstructure is the portion of the building situated above the ground and serves its intended functional purpose. The substructure or the foundations is the lower section located below the ground level which transfers the load of the superstructure to the subsoil. Hence, the foundation is the part of the substructure that directly contacts the ground to which the loads are transmitted. The soil immediately beneath the base of the foundation is known as the subsoil or the foundation soil, and the lowermost part of the foundation in direct contact with the subsoil is called as the footing. The primary function of a foundation is to transfer the dead loads, superimposed loads or the live loads and the wind loads from a building to the underlying soil in such a manner that settlement remains within permissible limits, avoiding cracks in the superstructure and the soil does not fail. When the loads are transmitted to the subsoil, it settles. If the settlement is minor and uniform throughout, the building will not be damaged. However, if the settlement is excessive or uneven, it can cause significant damage, manifesting as the cracked walls, distorted doors and windows openings, cracked lintels, walls thrown out of the plumb, and sometimes even the complete collapse of the building. Foundations are thus the most critical part of the building. As they are situated below the ground level, signs of foundation failure often become noticeable only after they have been already impacted the building. A foundation must be strong enough to prevent both excessive and uneven settlements. Unequal or differential settlements can be caused by weak subsoils such as made up ground, shrinkable and expensive soil like clay, frost action, groundwater movement and uplift pressure, excessive vibrations due to traffic or machinery, slow consolidation of the saturated clays and slipping of the strata on sloping sides. Therefore, these factors must be considered when designing foundations. So, what are the different causes of unequal or differential settlements? First is weak subsoils such as made up ground. Weak subsoils, often found in areas of made up ground, consist of loosely compacted materials that have not undergone natural geological processes. These soils can include fill materials from the construction debris, waste or loose sand. When a structure is built on these subsoils, the uneven compression of the ground can lead to the differential settlement. Over time, as the load from the structure compacts the weak subsoil, different parts of the foundation may settle at different or varying rates. This can cause tilting of the building, cracks in the walls and misalignment of doors and windows. Conducting thorough geotechnical surveys and employing ground improvement techniques such as soil compaction, grouting or using deep foundations can mitigate this issue. Second is shrinkable and expensive soils like clay. Clay soils are particularly sensitive to moisture changes. When clay gets wet, it expands significantly and when it dries, it shrinks. This cyclable swelling and shrinkage can exert variable forces on the foundation of the structure. The differential movement caused by the expansive soil can lead to significant structural damage, including foundation cracks, warping of the structural elements, and potential failure of the foundation system. Third is frost action. In cold climates, the freezing of water within the soil can lead to the frost heave. This process involves the expansion of the water as it freezes, causes the soil to uplift. When the ice thaws, the ground may not settle uniformly, resulting in differential settlement. Frost heaves can cause pavement to crack, foundation walls to shift, and the structures to develop uneven floors and walls. To prevent frost action, foundations can be built below the frost line and insulation can be used around foundations to maintain a stable temperature. Additionally, proper grading and drainage can prevent water from accumulating around the foundation. Fourth is groundwater movement and uplift pressure. Fluctuations in groundwater levels can alter the effective stress in the soil, leading to the changes in the soil bearing capacity. Groundwater movement can cause uplift pressure, which can lift parts of a foundation unevenly. Differential uplift can lead to cracking of the foundation, uneven settling of the structure, and potential structural instability. Ensuring proper drainage around the foundation, using waterproofing techniques, and designing foundations to withstand uplift pressure can help address this issue. Fifth is excessive vibrations due to traffic or machinery. Continuous vibrations from the heavy traffic, construction activities, or industrial machinery can lead to the gradual compaction of the subsoils, resulting in differential settlements. Vibrations can cause soil particles to rearrange and densify, leading to uneven settlement. These can cause structural damage such as cracks in the walls and foundations, tilting of the buildings, and misalignment of the structural components. Isolating the structure from the sources of vibration using vibration dampening techniques, designing foundations to resist dynamic loads, and monitoring the site for excessive vibrations can help mitigate this effect. Sixth is slow consolidation of the saturated clays. Saturated clays consolidate very slowly under load due to their low permeability. This slow consolidation process can lead to the ongoing settlement over a long period, which may be uneven. Structures built on saturated clay may experience prolonged or an uneven settling, leading to differential settlement. This can result in structural issues such as cracks, tilting, and even collapse if not properly managed. Preloading the site with additional weight to accelerate consolidation before construction, using weak drains to expedite drainage, and employing deep foundation systems like pile can help mitigate the risk. Slipping of the strata on sloping sites. On sloping sites, layers of soil or rock can slip or move downhill over time, especially if they are waterlogged or subjected to seismic activities. This movement, known as the soil creep or landslides, can cause differential settlement. Structures on sloping sites are at risk of differential settlement due to movement of the underlying strata. These cause significant structural damage, including cracking, tilting, and even collapse. Measures such as constructing retaining wall, using soil stabilization techniques, installing proper drainage system, and designing flexible foundations that can accommodate some movement can help manage the risk associated with the sloping sites. Now, the next is functions of the foundations. Foundations serves the following purposes. First is reduction of the load intensity. Foundations play a crucial role in distributing the loads from the superstructure over larger area, thereby reducing the load intensity at the base. This is essential to prevent excessive stress on the subsoil. In the case of the deep foundations, such as piles or caissons. The loads are transmitted to the deeper subsoil layer through mechanisms like side friction and end bearing. By spreading the load over a larger area, foundations can help to ensure that the underlying soil can support the structure without experiencing excessive settlement or failure. Now the next is even distribution of loads. Foundations are designed to evenly distribute the non-uniform loads of the superstructure to the subsoil. This is particularly important when dealing with structures that have columns or other load-bearing elements carrying unequal loads. For instance, a combined footing can be used to support two columns with different load intensities. The footing is designed to spread the load evenly across its base, minimizing the risk of unequal or differential settlements. This even distribution can maintain the structural integrity and stability of the building. The next is provision of the level surface. Foundations provide a level and firm surface upon which the superstructure can be constructed. This is fundamental to the construction process, as a stable and level base is necessary for proper alignment and stability of the entire structure. Without a level foundation, the superstructure may experience uneven settlement, leading to the structural issues such as cracks and tilting. Lateral stability. Foundations enhance the lateral stability of the superstructure by anchoring it securely to the ground. This is particularly important in areas prone to the horizontal forces such as wind or earthquakes. A well-designed foundation can help prevent the sliding and overturning of the structure by providing resistance against these lateral forces. This is achieved through various means such as increasing the depth and width of the foundation or using deep foundation systems like piles and anchors. The next is safety against undermining. Foundations ensure the structural safety of the building against potential undermining or scoring caused by the natural forces or activities. For example, burrowing animals or flood waters can erode the soil around the foundations, leading to a loss of support and potential collapse. Properly designed foundations, often with the additional protective measures like retaining walls or score protection, help to mitigate this risk and maintain the stability of the structure. The next is protection against soil movements. Special foundation measures are employed to minimize or prevent distress in the superstructure caused by the soil movement. Problematic soils such as expensive clays can undergo significant volume changes due to the moisture variations, leading to heaving or settlement. Foundations designed to counteract these effects include techniques like soil stabilization, the use of moisture barriers, and the construction of flexible foundation systems that can accommodate soil movements. These measures help to protect the superstructure from the cracks and other forms of damage. The next is essential requirements of a good foundation. A good foundation must be load sustainability. A foundation must be designed to bear all the type of loads imposed on it, including dead loads. Dead load is the weight of the structure itself, and the live load. Live load includes furniture, occupants, and other movable objects. The foundation must transfer these loads to the subsoil in a manner that prevents excessive settlement or the movement. If a foundation cannot sustain the loads, it may lead to settlement that can compromise the structural integrity of the building. This can result in cracks in the wall and floors, misalignment of doors and windows, and in severe case structural failure, that is completely collapse of the building. Proper geotechnical investigation is crucial to understand the soil properties and bearing capacities using appropriate foundation type. For example, shallow foundations like spread footings for lighter structures or deep foundations like piles for heavier loads ensure load sustainability. The next is rigidity. The foundation base should have adequate rigidity to distribute the loads evenly and minimize differential settlement, which can occur when different parts of the foundation settlement at different rates. Differential settlement can lead to structural problems such as cracking in the foundation, walls and other structural elements. It can also cause tilting or uneven floors impacting the functionality and safety of the building. Ensuring the foundation is designed with enough stiffness and strength to resist deformation. Techniques include using reinforced concrete, designing foundations with wide bases and connecting footings with grade beams to distribute loads more evenly. The next is adequate depth. The foundation must be placed at a sufficient depth to avoid issues related to soil moisture content changes such as swelling and shrinkage. Adequate depth ensures the foundation is below the frost line in cold climates to prevent frost heave and deep enough to avoid issues from the soil volume changes in expensive soils. Foundations that are not deep enough may be susceptible to movements caused by soil moisture changes leading to uneven settlement and structural damage. Conducting soil analysis to determine the depth at which the soil remains stable and unaffected by seasonal changes. Foundations should be designed to reach this depth considering local climate and soil conditions. The next is strategic locations. Foundations must be placed considering future conditions and potential changes in the environment. This includes accounting for the future construction, changes in groundwater levels and any potential environmental impacts that could affect foundation performance. If foundations are not strategically located, they could be adversely affected by the unforeseen future conditions such as construction activities nearby, changes in water tables or environmental degradation leading to structural issues. Thorough planning and site evaluation to understand current and future conditions that may affect the foundation. Employing flexible foundation designs that can accommodate potential changes and ensuring proper drainage systems are in place to manage water flow and groundwater levels. The next is durability. Foundations should be constructed from materials that resist deterioration due to environmental conditions such as moisture, temperature fluctuations and chemical reactions. The next is economic feasibility. The design and the construction of the foundation should be cost effective, balancing safety and performance with budget constraints. The next is accessibility for maintenance. Foundations should be designed to allow for inspection and maintenance to address any potential issues over the lifeline of the structure. Then the next topic is various types of foundations. Foundations can be broadly classified into two main categories. First is shallow foundations and the next is deep foundations. According to Terjaghi's criteria, a foundation is classified as the shallow if its depth is equal to or less than its width, or while a foundation is considered as deep if its depth is equal to or greater than its width. Each type of foundation serves different purpose and is suitable for specific soil conditions and structural requirements. So, the first is shallow foundations. Shallow foundations are commonly used for buildings and other structures where the load can be adequately supported by the surface layers of the soil. From a design perspective, shallow foundations can be characterized into several types, including spread footings, combined footings, strap footing and the mat foundations. Each type has its own unique design features and applications. So, first is spread footings. Spread footings are designed to spread the load of a wall or column over a larger area, thereby reducing the load intensity on the soil. This helps in preventing excessive settlement and ensures the stability of the structure. Various types of spread footing includes single footing for a column. This footing supports a single column. It involves spreading the loaded area of the column to a larger base area through a single spread of concrete. The base is generally made of reinforced concrete to provide adequate strength and durability. Stepped footing for a column. For heavily loaded columns, a stepped footing is used, which has multiple steps to distribute the load over a larger area. This design helps in reducing the pressure on the soil and provides better load distribution. Then the next is sloped footing for a column. This type of footing features a sloped concrete base which has greater thickness at the junction with the column and reduces the thickness towards the end. The sloped design helps in achieving a more uniform distribution of stress across the footing. Then the next is wall footing without step. This type of footing is a simple spread footing for a wall, consisting of a flat concrete base without any steps. It is commonly used for lightweight walls where the load is relatively low. Then the next is stepped footing for a wall. It is typically used for masonry walls. This footing includes steps to help distribute the load. The step design provides better stability and helps in reducing the differential settlement of the wall. Then the next is grillage foundation. It is used for heavily loaded steel stanchions. This special type of isolated footing involves a grillage of rolled steel joist embedded in the concrete. The grillage foundation spreads the load over a larger area and is particularly useful in areas with poor soil bearing capacity. It consists of two or more tiers of steel joist arranged at right angle to each other, providing a strong and stable base for the stanchion. Then the next type of footing is combined footings. Combined footings are designed to support two or more columns. They are used when the columns are closely spaced and individual footings would overlap, or when the loads from the columns need to be distributed more evenly. Combined footings come in various shapes depending on the load conditions. First is rectangular combined footings, used when columns carry equal loads. The design ensures that the center of gravity of the column loads coincides with the centroid of the footing area. This helps in achieving a uniform distribution of stress across the footing. Then the next is trapezoidal combined footing, used when columns carry unequal loads. This footing is trapezoidal in shape to evenly distribute the load. The wider end of the trapezoidal supports the column with the higher load, ensuring stability. Then the next is combined column wall footings. Sometimes it is necessary to provide a combined footing for columns and a wall. These footings are designed to take into account the load distribution from both the column and the wall, ensuring that the structure remains stable and secure. Then the next type of footing is strap footings. In situations where the distance between the column is significant, making a combined trapezoidal footing is impractical. Strap footings are used. Here, independent footings for each columns are connected by a beam. This strap beam does not transfer pressure to the soil but helps distribute the load uniformly across both the footings. The strap beam is designed to infinitely stiff, ensuring that the load from the columns are evenly transferred to the soil through the footing. Then the next is mat foundations or the raft foundation. A mat or raft foundation covers the entire area beneath a structure, supporting all the walls and the columns. This type of foundation is used when the soil pressure is low or the building loads are heavy, make it more economical than the spread footings. Mat foundations are particularly effective in soils with compressible properties as they help to bridge over these areas and reduce differential settlement. They are also used to reduce settlement above highly compressible soils by making the weight of the structure and the raft approximately equal to the weight of the soil excavated. Then the mat foundations can be divided into three types based on their design and construction. Solid slab system. This system consists of a large unbroken slab covering the entire area. It is the simple type of mat foundation and is used for structures with uniform load distribution. Then the next is beam slab system. In this system, the slab is integrated with the beams to provide additional supports. The beam helps in distributing the loads more effectively and increase the rigidity of the foundation. Then the next is cellular systems. This system consists of a slab with a cellular structure, providing enhanced rigidity and load distribution. The cells can be filled with concrete or other materials to increase the strength and stability of the foundation. Then the next is deep foundations. Deep foundations are used when the surface layers of the soil are not capable of supporting the loads of the structure. These foundations transfer the load to the deeper, more stable soil layers or rock strata. Deep foundations include deep strip, rectangular or square footings, pile foundations, pier foundations, and the well foundations. First is deep strip, rectangular or square footing. These type of footings are considered deep when their depth increases or exceeds their width. They are similar to the shallow strip footings but are used in deeper soil layers for added stability. Deep footings are often used for heavy structures where the surface soil cannot provide adequate support. Then the next is pile foundations. Pile foundations use vertical members, that is pile, to transfer the load to the deeper soil or rock layers. Piles can be made of timber, concrete or steel and are chosen based on the soil conditions and the load requirements. Pile foundations are used in situations where shallow foundations are impractical or uneconomical. Types of piles include end bearing pile. These piles transfer the load through water or soft soil to a foundation suitable bearing stratum. They are commonly used for heavy loads in multi-storied building, ensuring that the settlements are minimized. Then the next is friction pile. These piles transfer the load to a depth through skin friction along their length. They are typically used in granular soils where the depth to a hard stratum is very great. The friction between the soil and the pile surface provides the necessary support. Then the next is combined end bearing and friction pile. These piles use both end bearing and friction to transfer loads. They are commonly used in soils with a combination of granular and cohesive properties. Then the next is compaction piles. These piles compact loose granular soils to increase their bearing capacity. They do not carry loads themselves but can be made of weaker materials like timber or bamboo. The compaction process involves driving the pile into the soil and then gradually removing it while filling the hole with sand or gravel. Then the next is pier foundation or the drilled caisson foundation. Pier foundations consist of large cylindrical columns that support and transfer loads to a firm strata below. They differ from pile foundations in their construction method and are generally shallower. Pier foundations are preferred in locations where the top strata consists of decomposed rock overlying a stratum of sound rock. The types of various type of pier foundations include masonry or concrete pier, steel pipes filled with concrete, caissons with steel cores. Advantages of drilled caissons include load capacity. Drilled caissons are capable of supporting substantial vertical load, making them the ideal for high-rise buildings, bridges and other heavily infrastructure projects. Then the next is durability. The concrete and steel used in caissons providing lasting support, resistant to environmental factors like soil corrosion and water ingress. Then the next is flexibility. These foundations can be tailored to suit various soil conditions, depth and load requirements, ensuring a stable foundation regardless of the site challenges. Then the next is well foundations or the caissons. Well foundations are large box-like structures that are designed to be sunk into the ground from the surface to a desired depth. They are typically constructed in locations where the soil is weak and cannot bear the load of the structure directly on its surface. The foundations can commonly used in the construction of bridges, docks and other massive structures that are significant to the vertical and horizontal load. Its application includes in the bridge pier, quay walls and the large structures. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.